In today's video, let's discuss about an important piece of analysis we normally do either in device or circuit design, which is known as the Monte Carlo analysis. So what we'll do in this video is I'll discuss some of the fundamental concepts and look at some practical applications and implementation strategies to employ Monte Carlo analysis either as a device level or at a circuit level. Now, what happens is by embracing these methods, you're actually trying to bring in randomness to your simulation and trying to simulate what happens in the real world. So it gives you further insight and helps you build expectations at what you'd expect post manufacturing. So let's first discuss what the problem is, right? So one of the biggest problems we have is that real world semiconductor devices exhibit significant process variations that can dramatically alter their performance, right? And these variations we've looked at before can be either lithography imperfections, which happen during fabrication, or it can be due to non-uniform doping, right? Transistor to transistor, wafer to wafer, lot to lot, doping concentration can vary. Lineage roughness, especially as you scale down features, the gate, the contacts, etc., can start having lineage roughness, which means like the CD is changing, which impacts either the capacitance or the contact resistance. You also have what are known as random dopant fluctuations, and that's basically the dopants under the gate change, and that causes changes in the VT of the transistor. And finally, you also have gradients in real circuits, and these gradients are caused by finite resistances and finite heat capacitances. And so you can have voltage gradients, temperature gradients in a circuit or in a device, and you need to figure out how does that impact the performance of the device. So we work around this using the Monte Carlo analysis. So what we do in the Monte Carlo, to be brief, is we model the statistical distributions of all the device parameters, and then we run thousands of simulations. So what we're doing is we're essentially simulating real life. So we run thousands of simulations with randomly varied parameters, and then using those, we predict the yield and performance across the manufacturing variations. And this helps us do two things. It helps us identify what the worst case scenario might be based on the variations that you assume, and it exposes any vulnerabilities that you have in your design. Right? So once you know what the worst case corner of your design is, then you can go ahead and see if you need to redesign something in case it's failing when you run these Monte Carlo simulations. And so what we're doing is by simulating the statistical nature. So instead of doing a very definitive model based, what we're throwing in here is we're throwing a statistical feature in the model which kind of simulates the manufacturing process, and we can transform unpredictable variability into some quantifiable metrics. Again, remember that as the process matures, right, these models become more and more predictive. So initially you would start off, when you start off a process in the fab, you might start off with a pretty loose statistical model, and as you build the process, as you learn about more about the process, more about the variations that can happen, then you can build a model which closely resembles the actual manufacturing process. So let's take a step back and talk about what is a Monte Carlo simulation. So Monte Carlo simulation, very simply, and this is applied across various fields, it's not only semiconductors or VLSI design. This video caters specifically to the device or circuit part of the simulations, but it's in general a computational algorithm that basically does repeated random sampling. And what we do is we use this randomness to solve problems that might be deterministic. Now, this technique was named after, you guessed it, the Monte Carlo casino, because it relies on probability, right? So it is a game of chance, and that gave the name for this kind of a simulation. So what do we do in such a simulation? Is basically we define a domain of all the possible inputs that are representing system variations. And then once we know the domain, then we generate random inputs. and these would be based off a probability distribution. So you need to know a little bit more about how you're going to make the device, how you're going to make the circuit, what are the kind of variations one can expect. And this is not something that you can come from basic physics. This is something which is intended to build in a manufacturing variation in your study. And then what you do is you perform deterministic computation on these inputs, and then you aggregate the results and form statistical conclusions. So specifically for semiconductors, how would you set up a simulation for Monte Carlo? Is basically you want to predict, for example, how do process variations affect the electrical characteristics, say of the device or of the circuit. Many a times it's used to estimate yield before manufacturing. So given the history of the fab, you can set up some initial parameters so that even before the first silicon comes out, you kind of know what to expect in terms of yield. An important aspect of this Monte Carlo is it gives you sensitivity analysis. So it's able to tell you among all the multiple parameters that you've chosen, which is the most sensitive one. And so if that is critical, then you'd basically set up tighter controls, go and fix that particular issue to reduce the variation so that your overall variation of the circuit or device is reduced. It helps us quantify reliability and it helps us guarantee performance, right? Once you can predict performance or give a probability distribution with performance, then as a fab manager or as a process engineer, you can provide a certain guarantee for what you'd expect from the process. And very importantly, as a circuit designer, it helps you design, optimize your margins, and prevents over design. Many a times, designers tend to be pessimistic. You want your circuit to work in the worst case, and what ends up happening is you do something less than over design. So you tend to be overly cautious. What happens with being overly cautious is while that's good and gives you a high rate of success, it probably pulls you apart from competition. So if you want to be competitive in the industry, if you want to be competitive in your marketplace, you need to ensure that your design leads among all other competitors. So let's quickly look at the math behind the Monte Carlo analysis. So let's first start with defining a random variable x with some probability distribution p of x. Right? And knowing the probability distribution, know that the integral of p of x over the domain of x should be 1. And this p of x is the probability density function. So this is something you need to know a priori before you start the Monte Carlo analysis. And so it's important that you kind of have a handle of what the uncertainty in the system is. Right? And one common mistake, because normal is very easy and normal is something used a lot, you tend to assume everything is normal. While in most cases that's okay, you need to be careful because many a time, especially in semiconductor physics, distributions tend to be skewed to one corner or skewed to have a long tail. In that case, a normal does not approximate us, especially if those tails begin to determine your yield, right? So it's important to understand what is the right probability distribution to use when you model that particular variation. And you can also think about distributions which are essentially multimodal, that they have two peaks, if you will. So you need to look at how to do that. Again, as I said, normally we use normal when we don't know anything, but the more information you know a priori, the better your prediction becomes. Now, the convergence of Monte Carlo is basically, it comes from the law of large numbers. So if you have n independent and identically distributed samples which have been pulled out from a population with mean mu, then as you keep pulling more and more samples of this population, what you say is that the average of this tends to mu. So the larger the number of samples you put, the more closer you begin to look at the actual population, and hence you see that the average tends to mu as n tends to infinity. Now again, a very common mistake here is that, remember, this works only when you assume they're all independent, right? And many a times certain processes, especially as you start looking at circuit blocks, you'll see a lot of them have correlations. And when particular correlations exist, you're going to be wrongly determining the yield or the performance if you assume them to be independent. So again, as much as possible, try to use the right distributions, try to use the right covariances, etc. as you implement the Monte Carlo simulation. Now, the Monte Carlo methods approximate integrals by averaging functions. So you convert integrals into a summation. And again, this is how you'd convert it to a summation by breaking down that integral into n pieces. And the larger you make n, the more this approximates the integral. Basic math. And so if you're sampling it from a generic probability distribution, so you need to, so here this assumes a uniform distribution for x between a and b, in which case you know that every x is going to have the same probability of occurring. Suppose there's a specific probability distribution for that particular x, then you need to account that when you're doing the integral, and that's essentially going to be given by the summation of f by p. Now, again, a very important thing to keep in mind and a common pitfall is that certain regions are important for your operation, right? For example, if you look at the transistor, say the region close to a small overdrive is important, then you need to ensure that you have the right probability distribution for parameters in that. Else you're going to be predicting a wrong number. So knowing your probability distributions a priori again is important. Now, Monte Carlo is used to estimate the expectations, and the expectations of the function, which depends on the random variable, is basically estimated by taking the average over a large number of samples. And you just need to make sure that when you're doing this, you need to ensure that you're normalizing it using the right normalized probability distribution, else you'll end up creating biased expectations. Now, how do you know how many samples to do in the Monte Carlo, right? And so the statistical uncertainty is estimated and it's quantified by what is known as the variance. Right? And so if you have mu hat as a sample mean and sigma squared is the variance of x, then you see that the variance in the sample mean is inversely proportional to n, right, the number of samples. And so as your n increases, your variance in the mean reduces, which means the error in estimating the mean reduces. And so you see this error is proportional to square root of n, which means that if you want to halve the error, you need to go 4 times more in the number of samples so as to get an accurate prediction of what the mean would be. Now again, here it's important that you ensure you have the right variance, especially if you're trying to put confidence intervals. It's important to know what the incoming variance is. So if, for example, you underestimate the variance, then you're going to have an overconfident error bar, which might end up causing large number of fails during production. So the central limit theorem applies, and you know that as you start looking at distributions with a large number of n, the Monte Carlo essentially converges to the normal distribution. So if I take x minus mu, it's going to converge to normal distribution around the origin. And this helps you create confidence intervals. So since you can now assume your Monte Carlo simulation is normal, you can create confidence intervals, and you can figure out, okay, what is the probability that 95% of my die are going to work? What is the probability that 99% of my devices will be on target, right? And so that this, knowing it normal, you can start putting numbers for the percentages. Now let's look at an example at a device level. And similarly, I'm going to do one at the circuit level. So a common thing we use Monte Carlo is to estimate the VT variation, because as you remember, VT is an important parameter in the MOSFET, and drive current, off current, anything, the properties of the switch, the MOSFET switch, are dictated by this threshold voltage. So when you want to look at the variation of threshold voltage, multiple process steps can impact this threshold voltage. So a few of them I'll call out. One would be the channel length. And so one way is you can assume there's a 10% variation. Now again, process engineers go into a huge lot of effort to ensure that this variation is low as possible. But you can assume a certain variation, and typically that's modeled as a Gaussian distribution. The oxide thickness, remember, that's a deposited layer or a grown layer. And so there can be a variation in the amount of oxide that is present in the gate. And you see that as your EOT is reducing, even a 1-2 atomic layer difference can cause shifts in VT. So it's important to model the thickness variation. As I mentioned before, random dopant fluctuations in the channel region of the MOSFET can change the VT of the device. Especially if you look at metal gate technologies, and you see that the work function or the variation of the work function, depending on the crystallinity of the metal gate, that can cause a further variation in the work function and eventually the threshold voltage. And then finally, you also have interface traps, and those affect both the subthreshold swing and the mobility. Now, many a times these interface traps also are a function of aging, right? So aging models, for example, will incorporate that. But in this case, so the threshold voltage variation, you can make the model better by bringing in aging also. So you'll see what the variation would be at time zero and what happens as you use the circuit for a long time. And so how do you implement the simulation, right? So a typical flow would look like this. You define the nominal, so what is the target, and you define what are the distributions for these various parameters that you've assumed around that target. And then using a random number generator, you generate random instances of the device model, right? So you'll assume all these things vary and you'll generate random instances. And for each instance, you'll simulate it using identical bias conditions. And then you'd extract key parameters, say VTH, I-on, I-off, etc. for each simulation. Now, each simulation has multiple random instances. So in fact, simulating random variations in the device, if you will. And then once you have these are now your results, so you can analyze the statistical distribution of these results and confirm if they're normal or if they have tails or what have you. Now, what is the impact and why do we do this, right? So key thing, as I mentioned, is it quantifies the parameter sensitivity. So doing this will tell you exactly how much variation of the VT comes from L, how much of it comes from TOX, how much of it comes from random dopant, etc. And it also helps you predict the percentage of devices that would meet specifications for a certain distribution that you've assumed, right? So if you're saying it's not meeting, so okay, what are the things I need to tighten? What are the key parameters I need to go and control so that I can increase the number of devices passing, right? So those are things you can start looking at once you get the data from this analysis. And you can also identify what are the outliers, and these outliers are important because these are indicating where the chip or where the device might fail. Now let's look at a circuit level Monte Carlo. There are multiple instances, multiple places where Monte Carlo simulations are used. I'll give you one example each from analog and digital. So for analog, a very common use case would be the offset voltage in diff amp, right? And we've seen before that this offset voltage is critical because this is an error in the diff amp. Ideally, you assume the differential pair to be balanced. So any input voltage difference automatically appears at the output. But if there's already an input built-in offset voltage, then that's going to affect your output voltage. And this input offset is basically caused by the mismatch in the transistors in the differential pair. And so you can do Monte Carlo simulations to simulate the random variations in these match pairs and then use that to set what the input offset voltage would be for your particular technology. Right? And typically we have around 1 to 10 millivolts typically in technologies. Another example from the digital world will be clock distribution, right? So remember, you have clock going to multiple parts of the chip, and these clocks are going through various devices, various logic of varying depths, etc. And variation in the clock path essentially leads to a clock skew, can also cause jitter, which, as you've seen in STA, causes timing margins, right? And so you want to look at how do device variations, for example, you added a bunch of buffers, how do transistor variations on those buffers impact the path delay. And so this Monte Carlo analysis will help you essentially do that and give you confidence or give you the bars on what the variation would be. And so that is important because that informs how you're going to synthesize your clock tree and essentially how you're going to look at timing margins for your FSMs. And finally, another important application is SRAMs, right? And memory cells are particularly vulnerable because memory tends to be one of the densest part of process. And as you've seen, for example, the SRAM is very device dependent. You'll see the flash is again very device dependent. So variations in the device, variations in process affect the SRAM instantly. So it's important to understand and design the SRAM such that it is immune or less immune to, more immune to process variations. So critical parameter would be the static noise margin, which you analyze using Monte Carlos. You also analyze read and write failures, what are the probabilities of that, and it also helps you determine the yield of the SRAM because it'll tell you how many bits can fail in your array, right? And that Monte Carlo will help you design the cell, for example, or figure out, okay, do I need to do additional assist techniques so that I improve my bit yield? So let's look at a few considerations. So in a circuit level Monte Carlos tend to be a little bit more involved than device level Monte Carlos, primarily because you need to deal with variations which might be of two categories. You have something known as a local variation, which is nothing but the within die variation, and you have what are known as global variations, which can occur die to die or wafer to wafer. Additionally, you have to deal with covariance. For example, certain devices when placed close together may track each other more than devices which are placed farther apart. So you begin to see that if you're doing Monte Carlos, you need to account layout into your picture. So if you think that two transistors are next to each other, they're going to be correlated more than something which are, say, a few pitches apart, right? And this is why, for example, in differential pair, we tend to keep those two transistors as close together as possible because they're going to be correlated as much as you can. Temperature and supply voltage variations can also cause the circuit to change, right? So you need to include those also in your Monte Carlo. So this is on top of all the device variation that you have included. And as I mentioned before, aging effects can also shift parameters over time. So that's something also you need to add if you're eventually going to do Monte Carlos prior to tape out. Good part is most modern PDKs include statistical models, and so they are very regularly used prior to tape out to get an idea of what to expect in your product manufacturing phase. Let's look at a very simple inverter delay analysis, right? So let's say I want to see how to design an inverter, right? So say I'm working on a 45 nanometer CMOS technology node. I'm looking at FO4 loading, right? So these are some of the initial simulation setup that I'm doing, right? I have an input which has a rise and fall time of 100 pico. And so what are the parameters I'm going to vary? I'm going to vary the PMOS or NMOS threshold voltage, right? So the threshold voltage. So here again, I'm not going to go deep into, say, doping concentrations or channel length variation. The reason I'm doing that is because I want to keep the abstraction level to a slightly higher level because I'm looking at circuits. When I'm doing device Monte Carlo, I'm going to look at the process level abstraction. And so I'm hoping that this VT variation has the variations of the L, of the TOX, of the dopants built into this. Right? I can further add a channel length variation if I want. Gate oxide thickness I can add. Load capacitance, right? Depending on how I'm driving the next inverter, there can be an additional variation in that. And so what are the things I'm going to measure? I'm going to measure, say, the high to low propagation delay and the low to high propagation delay. And so suppose I've run these 1000 Monte Carlo simulations. Say I observe something like this. I see that my high to low delay has a mean of 45, a standard deviation of 3.8, and a min max of so. So this is over 1000. As I do more simulations, I'm going to get the distribution to be tighter, right? And what you see similarly, or the distribution converge to what the actual variation in the process would be. Similarly, I'll have a low to high distribution of, say, a mean of 52, standard deviation of 4.2, and a min and max. So inherently in my design, for example, I've set it up in such a way that the high to low and low to high are different, and that's because of the differences in the NMOS and PMOS. Right? The way, for example, the mobility impact is going to be different. The sensitivity to threshold voltage is going to be different because doping densities might be different. So the NMOS and PMOS will not essentially behave identically. They'll tend to behave in different directions. And so what are the key insights I develop from something like this? What I see is that if I want to use this inverter, then I need to budget for a timing margin of at least 3 sigma. So this gives me the sigma, and I'm going to use 3 sigma of this just to ensure I get up to 95% margin, right? And so I take the larger of the two and take 3 sigma of that. So roughly 12 to 13 picoseconds I'd use for a 99.7% yield. And then what I also get is maybe I should change my PMOS sizing if I want to balance the rising and falling delays. And what this particular simulation shows to me is that the parameter sensitivity analysis shows that the VT variation is the largest reason for this variation. So if I'm going to go and build the process, I'm going to try and figure out are there process techniques by which I can reduce the variations of VT, and that should help me reduce the variation in the particular inverter. Now, an important aspect of Monte Carlo is used a lot in yield estimation, especially before it goes into the fab, right? And yield can be of multiple types. There's what is known as functional yield, that is how many of the circuits operate correctly. There is what is known as the parametric yield, that is how much of this proportion meets performance specifications. And third is the reliability yield, that is how many of these circuits actually perform reliably through the end of product life, right? So this would be the first yield, right? This has to be met before you start talking about this, and these two have to be met before you start talking about this. And so yield is typically given by passing them samples by total number of samples, right? And so doing this kind of analysis, you get multiple useful informations, right? It gives you an idea as to where do you center the design. For example, how do I center the design, or how do I set the nominal design so that when I put in variation, the entire design performance fits within the specification limits. It also gives me clues of, suppose I need to tighten the distribution, what are the kind of design techniques I need to use to reduce the variability? Right? Should I use larger devices, redundancy, what do I have it? Also, this gives you an idea as to what is the kind of margin I need to build into my design so as to ensure that all my expected variation is accounted for. And then an important part which is used a lot these days is what are the kind of circuits I need to implement. These are known adaptive techniques. We saw a few of them in the VLSI lectures. What are the kind of circuits I need to implement? That is, even if there are variations in the performance of certain circuit blocks post manufacturing, how do I compensate for that, right? So these again help you meet your yield specs, help you meet your product reliability specs, right? So to summarize, Monte Carlo is a very important technique. It's used very, very commonly in the industry, and it's a useful tool to understand the limitations or the performance that you can expect from your manufacturing process.